Good morning, everyone. I am Professor Saraswati Pandey. Today, we are going to discuss the construction working principle of the transformer. So, what is transformer? Transformer is basically a magnetic circuit. Now, what is magnetic circuit? Magnetic circuit is a closed. What is circuit? Circuit is a closed path, basically through which the current flows. So, in magnetic circuit, it is a closed path through which magnet can flow. So, this is a circuit diagram for magnetic circuit. To create a magnet circuit, we need a ferromagnetic material over which we are going to wound a conductor, and where if we pass the alternate current mmf is induced, and because of the induce of mmf the magnetic flux line is created, and due to the ferromagnetic material over here the flux starts flowing in the circuit, and this is how the magnetic circuit has been created. In magnetic circuit, flux are the quantity which flows, and in electrical circuit the current is the quantity that flows. So, as we can relate the magnetic circuit with the electrical circuit. As you can see, the quantity which flows in the magnetic circuit is the flux, and the quantity which flows in the electrical circuit is the current. Similarly, you can see to for the cause for the flow of current is the EMF, that is electromotive force, that is potential, and in the cause of flow of magnetic flux is MMF, that is magnetomotive force. As we know that in an electrical circuit there is a opposition to the flow of current by the resistance. Similarly, in the magnetic circuit there is a opposition to the flow of flux, and that is known as reluctance. Similarly, the permittivity tells the conductivity of the conductor. Similarly, the permeability tells how good the magnetic flux can flow in the magnetic circuit of the material. Okay, now the basic definitions we can move. Magnetomotive force. Magnetomotive force is a driving force in a magnetic circuit analogous to the electromotive force in the electrical circuit. It is generated by a coil with a current, and it is given as N into I, where N is the number of turns of a coil, and I is the current flowing through this coil. Now, magnetic flux, it is the total magnetic force line passing through a given area. It is known as magnetic flux, and it is very much similar with the electrical current in the electrical circuit. Reluctance is the opposition to the flow of flux. Permeability is a property of a material that indicate how easily flux can pass through it. And absolute permeability, and there are other two parameters: absolute permeability and relative permeability. Absolute permeability, the permeability of a specific material measured in henries per meter, and related the ratio of material absolute material to the permeability of air gives the relative permeability. Now, flux density, the amount of flux per unit area is known as flux density. Whenever we are going to measure the flux by the boundaries, that is the area, we are going to get the flux density, magnetic flux density. It is denoted by capital B, and it is given by flux per area, and its unit is Weber per meter square. Now, magnetic field intensity, it is a ratio of magnetomotive force to the length of the magnetical path. It is basically mmf by L, as its unit is ampere turn per length, and it is measures the strength of the magnetic field. Okay, permeance is the conductivity. As we know, in an electrical circuit there is a conductivity. Similarly, the permeance tells the conductivity of the magnetic material. So it is a reciprocal of reluctance. It represents the ease with which the material conducts the magnetic flux. Now, if we are going to understand the transformer, the basic definition, that is self-inductance and mutual inductance, I need to be uh, understand first. So what is self-inductance? Suppose this in this picture you can see it is a coil, and it is wound in some, say, ferromagnetic material, and in this coil alternating current is passing. When an alternating current passes through a coil, in this coil an mmf is generated, that is magnetomotive force. Due to this magnetic motive force, magnetic field is created, that is the magnetic flux of line. And when this magnetic flux is created around this conductor, you can see this magnetic flux line will try to link with the conductor. And when this magnetic flux will try to link with the conductor will oppose the linkage of this magnetic flux through it. And due to this opposition, EMF is induced. Now this EMF, that is the work done to oppose the magnetic flux, is known as induced EMF. And this EMF is induced because the magnetic flux are trying to link with the conductor. So the opposition is taken by self by the coil. So this is known as self inductance. And this is the diagram for the self inductance. Now mutual inductance. Now take two coils which are being very closely placed, and to the one coil we are going to give a supply of alternating nature. The alternating quantities are the quantities which change their parameter, which change their value at a fixed interval of time. So when this alternating voltage is connected, an alternating current starts flowing in this conductor. And when the alternating current starts flowing in this conductor, in a sim as in the self inductance, and mmf is created, and due to this mmf magnetic flux is created, and this magnetic flux will try to penetrate, and this magnetic flux will try to move as this second coil, which is having a number of turns n2, is placed nearby. The magnetic flux will try to link in this coil. As the flux coming in this coil is alternating in nature, and emf will induce, which will be alternating in nature. Because of the induced EMF from of the first because of the first coil, an EMF is induced in the second coil. And as this EMF induced is of alternating nature, the magnetic flux, the current, alternating current is also created in the second coil. Due to this alternating current, mmf is created in the second coil, and magnetic flux are created in the second coil. And due to this magnetic flux, the flux will try to penetrate in the first coil. And because from the first the EMF is created in the second side, and from the second the EMF is created in the first side, this is creation of of inductance is known as mutual inductance. It is also measured in Henry. Now, single phase transformer. Single phase transformer is a magnetic circuit. And this magnetic circuit, we know in this magnetic circuit, the flowing quantity is the flux. And this is a single phase transformer, and it is AC to AC machine. It is a static device. Static means it has no rotating parts. It's the simplest machine which we can say. And AC to AC means whatever the signal which we are providing is of AC nature, so at the output also you are going to get the AC signal only. So from this construction, I can from the overview or the pictorial of single phase transformer shown in the figure. This figure indicates a block of ferromagnetic material. Basically, these blocks are a slice of rectangular coils that are aligned one by another by varnishing with some thick viscous liquid like grease, and they are intact or assembled together. And in that assembly, the conducting wires are wound on both the sides. So at one side, you can see a supply, that is input voltage is provided. The side at which the input signal is given is known as primary winding or primary coil, and the coil at which you are going to take the output is known as secondary winding or secondary coil. Now, when the current will flow in the when you give the supply of alternating nature, current will flow in the coil, and because of the current flow, mmf is going to induce, and because of that mmf, your magnetic field line are going to be created, and this magnetic field line are going to move in this magnetic circuit, and they are going to link with the secondary side. And in this secondary side, you can see, and in the secondary side you can see that the flux is going to link, and because this coil is made up of conductor, it is going to oppose the flow of the flux through it, and because of this all process, emf is going to induce. And the flux is of alternating nature, so the induced emf is also going to be of alternating nature, because of which an alternating current starts flowing in the coil. This alternating current will create an mmf in this coil, and magnetic flux are going to create, and this magnetic flux are going to link with the primary side, and this is how your Magnetic single phase transformer work in the and the working principle for the single phase transformer is mutual inductance. This is the basic definition or basic working of the single phase transformer. And the single phase transformer is based on the Faraday's law of electromagnetic induction. When AC voltage is applied to the primary winding, it creates a time varying magnetic flux. This flux linked to the secondary winding and induce the magneto electromotive force. A single phase transformer operates on the principle of Faraday's law of electromagnetic induction, especially mutual induction. When an alternating current flows through the primary winding, it creates a changing magnetic flux in the core. This changing magnetic field then induce a voltage in the secondary winding, allows the transfer of electrical energy between the two windings. And as transformer are related, we can consider the transformer as ideal, but actually no machine or no appliance is ideal. In all the appliances or in all the electrical or electronics gadgets, they are associated with the losses. So a transformer does not require any moving parts to energy transfer. This means that there are no friction or winding losses associated with the other electrical machines. However, the transformer do suffer from the other type of losses called copper loss or iron loss. As transformer is a static machine, it is fixed at one position, it doesn't move. So the mechanical losses are not associated with the transformer, but there are losses which are associated with transformer is the iron loss, and a second one is copper loss. So copper loss we all know is related with the flow of current. When a current flows through the circuit, it is associated with the loss, that is I square RT, that is the heat energy is dissipated from the machine or from any appliance where the current flows. And coming to the iron losses, as we know, the transformer is a electrical circuit, it is a magnetic circuit. So the and magnetic circuit is made up of ferromagnetic material, most commonly iron steel or silicon steel. So iron loss is associated, and there are two types of iron losses. One is hysteresis loss and other one is eddy current loss. When the flux overloaded in the transformer circuit, there is a flow of current in the magnetic circuit itself. Rather than flowing of flux, their currents also start flowing in that ferromagnetic material, and that current flows in a circular motion, and that is why a name given to that particular losses eddy current losses, and that took place in the ferromagnetic material or core of the transformer. So this is a iron loss. The another loss is the hysteresis loss. Hysteresis loss is the lagging of the magnetic molecule within the core, and is in response of the alternating magnetic flux. The lagging condition is due to the fact that it requires power to reverse the magnetic molecule, and this type of loss is known as hysteresis loss. Okay, thank you.